All right, welcome back to the last lesson for the week, which we're going to be looking at how to prepare solutions. Now, the sad thing is, of course, where we can't actually get our hands on the glassware and prepare the solutions for ourselves, but we still kind of need to know the theory behind it, the general procedures, and I'll try to upload a video of with the actual glassware and actually how to prepare it and stuff like that. For the reason for this is sometimes you will be given a lot of information, and of course you'll need to know in general how to prepare a solution. And for a lot of chemists, a solution is, or how to prepare one is one of those basic laboratory skills that is really needed. And I know when for Chem 30 in the first week of classes, we normally do make solutions because you'll even need to know how to prepare a solution to perform a particular lab if you do continue on with chemistry. So these things are very important. So of course, first of all, we have to get a little definition out of the way, and what is a standard solution? So standard solution is just a solution with an accurate known concentration. So these are generally made with extreme care, and then of course we do have very pure substance, so when we do have a concentration, we know it's going to be true. So the term standard refers to a set value considered to be true, which from all others are going to be compared. So this is normally the actual concentration value in a question, or it is the solution that I generally make for you, because I do take extreme accuracy when I try to make solutions. So these standard solutions must be mixed with extreme accuracy, and of course you need to know the labware that'll be there. So I'm going to upload a PDF that has the laboratory equipment on it. So if I talk about the Erlenmeyer flask, the beaker, the pipette, and stuff like this, you can just upload that and have a look to see what those particular pieces of laboratory equipment look like, just for your own knowledge, and just so you're not see a word and you're like, oh, what is that, right? You'll kind of have an idea. Now, gases are not going to be discussing this right here. We are going to mostly talking about stuff from a solid or a concentrated solution. Trying to make a standard solution out of gas is extremely difficult, and we generally don't do it. So first, we're going to look at preparation of a standard solution from a solid reagent. Now, these are the most common just because most chemicals, if you can get them in their solid form, and all ionic compounds are solid to begin with, they're easy to transport, easy to handle, and then of course easy to weigh out as long as you have a weigh scale. So because of that, if we are dealing with a solid, first we must calculate the amount of mass required to get the desired concentration. Then we're going to mix that amount carefully with water in the following steps outlined below. So of course, first step is we actually calculate the mass of solid required, right? We have to know if we want to make a 1.0 moles per liter solution of, let's say, sodium chloride, well, we have to know exactly how much we need, right? So we're going to calculate the mass required. After we calculate it, we're actually going to weigh it out. Weigh the required mass of solute in a clean, dry beaker. So beaker is where we do all of our mixing. Now, next, we are going to dissolve the solid in distilled water. So use distilled water so there's no other ions present inside until we get about half the final volume that we are trying to make. So for example, if we are trying to make a liter solution, we're going to try to dissolve it in about 500 milliliters of water. Now, once we have it fully dissolved, we are going to transfer the solution to a clean and dry volumetric flask. Now, the reason we're using something called a volumetric flask is these flasks are designed specifically to hold only one volume and one volume only. So they're made with extreme accuracy and are generally really expensive. So if you have a volumetric flask that is designed to hold 100 milliliters, that means that there's going to be one measurement line on it, and you read it until it reaches 100 milliliters, and that's it. Now, once we transfer our solution to that clean, dry volumetric flask, we're going to rinse out the beaker about 3 times with small amounts of water, and this is just to ensure that we get every single last bit of that solution inside of our volumetric flask. And I always like to use the analogy, imagine just kind of if you drink a glass of milk, you know that you can see milk residue left on the side of the container. solutions are going to be the same thing, so you have to rinse it out and kind of transfer it just to get every single last bit of that solution inside the volumetric flask. Once we do that, we are going to fill the flask, fill with water, until the bottom of the meniscus is on the calibration line. So if you have meniscus, I know somebody who's like, isn't meniscus part of the knee? Yeah, it is. That's the human meniscus. But for chemistry of meniscus, if we just flick over to the other page, the meniscus explains right here. So it's a shape that liquid makes when it's formed in a very small tube. So it is the result of cohesion and adhesion of liquid molecules. So if you think back to Science 10 with water as it gets transferred to a plant, when you definitely heard those words. And it's the cohesion and adhesion between liquid molecules and the size of the container that it generally takes to shape. So liquids can form two different shapes, concave and convex. So we have two shapes right here. Now when we're looking at it, so we always measure from the bottom of the meniscus. That's what we're talking about right here. So for example, when it says the bottom meniscus on the calibration line, so if we have a volumetric flask, now I'm just going to draw this for you guys in a different thing right here. So a volumetric flask generally looks like this, where it has an extremely long, narrow neck, and then it has a bulb on the bottom. And you might have seen these kicking around in a classroom. And there's always just one line right here. So this is a calibration line. The calibration line is always somewhere in the neck. So what it's asking is that you try to get the meniscus so that U-shaped, so it just sits on top of the calibration line, just like that. So it's not above, not below, but it sits right up on top. And then of course our solution is all inside here. So that's what that part is saying right there. And once we get that, we are going to cap it or cover it and invert several times to mix. So that is how we make a solution from a solid reagent. Now, of course, what is meniscus? Now, when we are reading as well, this is just kind of a little example when we're reading. Always have a look at the measurements so we can tell 6, 7, 8. You want to look at in between right here. So 6, and we can tell 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So we can tell the bottom of the meniscus right here is on that 6.6. So I'm just going to erase that right here. It's like, for example, this is 6.60 milliliters. And we always estimate the last value when we're reading something. We can tell it's exactly around 6.6. That's why we're saying 6.60. And that's just kind of a little bit of practice with reading the meniscus. Now the equations that we're going to be using, of course, concentration, we will need this one. And then, of course, if we are weighing something from a solid reagent, we will need this one right here, mass and molar mass equation. Now, for these right here, this actually goes into basically everything we've done before. So there's really nothing new with regards to calculations. We've done these in calculation, so I want you guys to actually pause this video and see if you can get the answer for this. Where it says mass of lead 2 nitrate must be used to produce 350 milliliters of a solution of a concentration of 0.125 moles per liter. All right, so pause the video, see if you can actually get the mass for this one. I'll put the answer up in 3 seconds. And when we plug everything in, we kind of get something that looks like this. So I wrote here all the given. So mass was the unknown. We had concentration, we had volume, and we had molar mass. So obviously, first step is always finding the number of moles. And in this case right here, we had concentration and volume. So we have number of moles, concentration times volume, and we get this number right here. And then finally, of course, mass is equal to number of moles times molar mass, and we get 14.5 grams. All right, so if you're still not sure on how to solve these here, go back and look at the video of concentrations, specifically the molar concentration one, and we've done one exactly like this. And of course, there is a lot of practice ones inside your workbook that you should be going through as well. Now, the next one, preparation of standard solution by dilution. So this one is a little different, so you might need to use the dilution equation, which is a new equation for us, but that's fine. So first of all, we have to figure out what dilution means. So what we have right here, dilution is the process of changing the concentration of solution by adding more solvent, right? Usually water, that's our normal solvent, to the existing solution. So during the process, the volume increases while the concentration decreases. So we have an inverse relationship. So the dilution equation is C1V1 equals C2V2. Now the reason we can use this equation is because the number of moles aren't changing. We're only adding water, so we're not changing the amount of solute, just the volume. So of course, while doing this, we will need to use this equation, but this is kind of a typical problem where we have what volume of concentrated hydrochloric acid. So the concentration of concentrated hydrochloric acid is 11.6 moles per liter. Now this is also on the back of your periodic table. I don't know if I have it right here. Nope, I do not have it uploaded to this one right here. But just check the back of your periodic table. I think it's on the left-hand side, kind of in the middle. There should be something that says common concentrations of concentrated solutions or something like that. And you'll see hydrochloric acid is 11.6. So a bottle of concentrated hydrochloric acid, this is the maximum it can be, is 11.6. So what volume of concentrated hydrochloric acid is required to prepare a 1 liter solution with a final concentration of 6 moles per liter? So we have C1 is our concentrated hydrochloric acid. We have V1 is equal to, well, what volume of it? We don't know. C2, we're making a 6.00 moles per liter solution, and in total we are making 1.00 liters of it. So this another one is kind of like Boyle's law, and essentially Charles' law as well from our gas units. As long as we have our units matching, we don't need to constantly have like everything needs to be in liters, everything needs to be in moles per liter, as long as the units of everything inside this equation matches. So our equation C1V1 equals C2V2. So of course we are trying to isolate for V1. So we do need to rearrange this equation. Now these are multiplied together, so remember when things are multiplied, in order to rearrange, we divide by the unwanted one. This will cancel out our C1s, and we are left with V1 is equal to C2, V2 all over C1. When we plug in our information that I have written down over on the left-hand side here, we get an answer of 0.517 liters, or 517 milliliters. Either answer is okay. I'll accept both. For the most part, a lot of the glassware in all the chemistry setting only goes into milliliters, so we'll kind of go to milliliters, but both answers are definitely acceptable. Alright, so that is using the concentration equation. Now for making a solution, obviously we will need to use this at some point. Just like the first one, making it from a solid reagent, we needed to calculate stuff, so we will need to calculate things here as well. So let's look at the steps. So what we have is our first step. Same thing, calculate the volume of the stock solution required. Now stock solution just means that it's the concentrated solution that we're just getting our thing from. Now once we calculate the volume of it, what we're going to do is retrieve our volumetric flask, but we're going to add distilled water until the volumetric flask is half full. So we're not putting the stock solution in there right away. And the reason for this is safety, because sometimes if you add water onto concentrated acid, you get a very violent reaction. You could get acid sprayed up in your face. Not a good thing to have if you have concentrated acid. So this way, if we put water in the flask first and we add the acid into it, it's just a safety precaution to make sure that we don't get acid in our face and all over the walls and all over everything. So this step right here is a safety. It's a safety step, but very important. So once we add the water to the volumetric flask until it's half full, now we are going to collect the required volume using a pipette. And the reason we need to use a pipette is that they are extremely accurate. So these pipettes come in two flavors, volumetric and graduated. Depending on what you need, you can use both. but you have to make sure that you use a pipette in order to get those. Now, once you collect it inside your pipette, you transfer the stock solution to the clean volumetric flask, fill with the water. Once it's all in, we add distilled water until the bottom of the meniscus, it's a hard word to say, bottom of the meniscus is on the calibration line. And then we finally cover and invert several times to mix. So this is just kind of another example where a student's told to prepare a 200 milliliter solution with a concentration of 0.1 molar per liter, and the teacher provides a stock solution of 0.5 moles per liter. So what volume of the solution must be used? So I just want you guys to try to pause this video right now and see if you can get the answer for this one using our new equation, C1V1 equals C2V2. And the answer is going to go up in 3 seconds. And we get 40.0 milliliters. So if you never got that one, just keep working around it until you get that answer. But that should be the answer to this particular question. Now, of course, the reason for this is oncoming test quizzes, stuff like this. I will expect you guys to be able to describe the procedure required to actually prepare a solution, because like I said, it's extremely important for chemists to be able to do this. It'll be important for Chem 20 if we do get a chance to get back and do more labs. If you plan on taking Chem 30 or any type of science where you might need it, being able to make a solution is super handy. So just be familiar with these steps, being able to write them out. They're only 6 steps and they're very similar, but that'll be super handy for the future. So that is it. Please definitely go through, continue your workbook section on these calculations. And of course, if you have any questions, make sure to bring them to Thursday for our Google Meet sessions, or of course, email me and hopefully we can figure stuff out. But anyway, that is it for this week's lessons. Make sure plenty of practice, and then next week we will be starting our acid and base section for this unit. So anyway, see you guys next week and have a great week.